So now we're going to talk about basically rotation of compliance tensors. So we've done rotation matrices, but now how do we actually rotate our compliance tensor? So remember, we have this relationship with strain, second rank tensor, compliance, fourth rank tensor, S, even though it's compliance C, related to stress, second rank tensor, and stress related to our stiffness tensor, C, fourth rank tensor. We have these equations. So we know how to relate one to another, but how can we actually rotate our compliance or our stiffness tensor? So we actually have these really nice equations, these 6x6 matrices that allow us to rotate. And so we can use these around each of the axes to rotate either stress or strain and actually obtain those values. So you can see very similar to the expressions that we've worked with previously. So I can rotate around, as I look at YouTube, I can rotate my new stress tensor based on these new, again, around one particular axis. So it's just another tool that we can use before. So we can actually take our old stress, write it in what we called a Voigt notation. So it's this 1x6 column. So we can look at basically a metal, and we have our compliance tensor right there. We can look at doing any rotation around the axis. So remember, last time we were in plane stress. So we can actually rotate. Actually, so remember it's T stress 3 dot R, basically our Voigt stress. So I think it's stress S Voigt. There we go. So if we go to our 19.3 degrees, remember that was our principal stress state, we see 16.4, 3.6, and basically no shear stress values as we got previously. Again, it was 19.29, but again, we're working with that kind of that same value. We're getting that same expression here. So you could do the exact same thing for strain. You know, again, if we plugged in 0, we get the same value back as we kind of saw previously. So we can use this new notation to calculate stresses as well. Again, it's another way to kind of check it. Remember, this was, if we did that rotation around basically that minus 25, we got close to our principal or our maximum shear stress value. So you see they're close to 10, 6.4. Again, everything's right in the universe when we can basically calculate these things multiple times. We can actually also calculate our strain in our Voigt, as you can see here. So in our original coordinate system with that stress applied, this would be our strain values. We can also do, again, rotations of our strain as well if we would want to in order to calculate those values. Here, again, remember, if we want to get realistic values of strain, we need to remember that those are in megapascals, so we could kind of calculate those out, just times 10 to the 6. But now we have more reasonable strain values as well. So we have our strain, we have our stress. We could also relate those using our expression as well. So, again, we calculate a new strain value. Here, we can also see below, this is where we're going to actually rotate our compliance tensor. So you could actually rotate that compliance tensor itself and get new values of either stress or strain, again, depending on where you're rotating and how you're rotating into the system. So you can actually calculate and rotate that out. So we can take again, you see it's our strain in the 3 times your original, or basically you could do that rotation here. So this would just be a new rotation. Actually, it's not T strain 3. We actually have to do our, we need to make a little quick correction here. It's not the strain Voigt. We have a little, yeah, exactly. Oh, there's the error. I see. So let's do that in, reevaluate. There we go. So you can see here, again, we have some values. There is that kind of, basically a little lower strain. But again, that would be our basically principal strain values that are associated with that. You can also calculate it using that rotation as well. So there's multiple ways essentially to skin a cat here. So you can rotate your compliance tensor and solve problems. It just really depends on what you're given, and you can kind of solve for unknowns here. But this is going to allow you in order to rotate that value. So if I want to rotate my compliance tensor, T-strain dot my original compliance tensor, and now this is important. This is an inverse. So it's not a transpose, it's an inverse value. So let's go a little bit further up. Actually, we can go here. So remember, this is an inverse. So inverse of T, basically stress 3, and voila. And then you could plug in again for any value. Theta goes to 19.3. And if you, again, now I could take this and I could actually, in order to get my new strain, I could just dot this S prime by my sigma prime, which would be this, the T dot stress. So my new stress. And what do you know? So I could either rotate my strain, or I could use that relationship that E prime is equal to S prime times my sig prime. The sig prime is that input 32 right there, and we've got our system. So you could do the same exact rotations around the 2 axis. You could do the same around the 3. We did it, and as you see here, and you could also do it around the 1 axis here. So that notebook will be available to you, and that's how you're going to rotate. And next time we can get into composite mechanics discussions. See you then. Thanks.